Hello everybody. In this video I want to take a look at question 48 and show you guys how we can use figure 6.29 here to quickly and easily write down the electron configuration for a neutral atom, and that's very key. This isn't going to tell us the ions. It will be the first step in figuring out the ion electron configuration, but we can only read off of the table directly a neutral species electron configuration. So the first one here is going to be a relatively light element, carbon. And the first thing I like to do is just write down that symbol there so that I know which electron configuration I'm going to talk about. Then I'm going to come down here and I'm going to locate the carbon on the periodic table down here. If I look beneath it here, it says 2s2, 2p2. So that's going to be the valence portion of the electron configuration. So I'm going to leave some space here, and then I'm just going to copy down exactly what that says. It says that we have a 2s orbital. It has 2 electrons in it, and there is a 2p orbital that has 2 electrons in it. Now what I need to do is figure out the core part. Okay, if this is the valence part, the part that's furthest away from the nucleus, what is the configuration of the part that's closer to the nucleus that's not going to be participating in chemical reactions, those core shells? To do that, what I'm going to do is I'm going to go up one row and over to the nearest noble gas. In this case, it's going to be helium. I can fill that in here as the abbreviated form, where I say that it has a helium core with this valence portion right here. Now, this says that it does not want the abbreviated form. It wants the full-on electron configuration. To get that, what I'm going to do is I'm going to come down here and I'm going to replace this helium core with what that abbreviation is really standing for. What it stands for is the portion that's right underneath helium here, 1s2. So I can come here and say 1s2, 2s2, 2p2, and now I have the full and the abbreviated electron configuration for carbon. Now, the next thing that we're going to want to do, and they're not asking us for in this question to do this, but the next bit of information we're going to want is how many valence electrons does carbon have here. So if we come down here, we have a couple of rules here. We have the valence electrons for a main group elements are those with the highest N level. And that's exactly what carbon is. It's a main group element because it's in this block right here. This is one of our main group elements. So the highest N level. So these coefficients here are the N levels. So the highest N level here is 2. These superscripts here are going to be the number of electrons. So there's 2 electrons in that orbital, and there's 2 electrons in p orbitals, for a total of 4 valence electrons for carbon. And this is a thing that's never going to change. Carbon's always going to have 4 valence electrons. Alright, now that we've done the simplest case, let's erase this away for a second, and we're going to come down here and try phosphorus, a little trickier example here. get rid of this. We're going to start the exact same way. We're going to come down to our table. We're going to recognize phosphorus is right there. I'm going to come up here. I'm going to write down the symbol for phosphorus, P, and its valence portion right there, 3s2, 3p3. Then I need to go up and over to this guy right here, neon. So this guy has a neon core. Now, last time we were able to just replace helium with 1s2. The reason we were able to do that is because helium is the highest one. Okay, it's the highest up here. It's only made out of this 1s2. We're going to have to do something a little different in order to get the full electron configuration this time. What we're going to need to do is to replace neon with this, and then just like we added neon onto the phosphorus, we're going to have to add helium onto the neon. So neon has a helium core with 2s2, 2p6, that's the portion I read right off of here, and then we need to finish it off with the valence portion for phosphorus that we know that it has. I'm sorry, I started writing something else there for a second. 3p3. Okay, so 3s2, 3p3 came from the valence portion of the phosphorus. 2s2, 2p6 is the valence portion for the nitrogen. And we know we have this helium core. And just like we did before, we're going to replace that helium core with 1s2. And we get 1s2, 2s2, 2p6, 3s2, 3p3. This is going to be the full electron configuration. This would be the abbreviated and this is just nothing. This is just an intermediate that we used to get to the full electron configuration. Okay. Oh, we did forget something though. Let's take a look at this 1 second here. If we look at this phosphorus, it's again in the main group. We need to be looking for the highest n level, so that's when n is equal to 3. These two electrons are valence electrons, these 3 are valence electrons, so phosphorus is going to have 5 valence electrons, and again, that's always going to be true. It's always going to have 5 valence electrons. Okay, let's take a look at vanadium. Vanadium's going to be a little bit different. It's down here, so we're talking about a transition metal now. Okay, but the way we go about getting the electron configuration is no different. What we're going to do is we're just going to write B like we always did. We'll look right here. It says 4s2, 3d3. So that's going to be the valence portion here. 4s2, 3d3. And we're going to go up 1 row all the way over to here to argon. And we're going to say that this guy has an argon core. And then we're going to play the same exact game that we did before. Argon is neon with this portion right here as its valence. So it is neon with 3s2, 3p6. We still have this valence portion here that needs to get carried down. And neon is 2s2, 2p6 with a helium core. And then helium is 1s2. So the full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. This is going to be our full configuration, and this would be our abbreviated. And you can see why we have an abbreviated version at this point. Like, we're really just going to wind up with long strings here, and largely we're just going to be replacing the same kind of pattern over again. It's going to be 2s2, 2p6, 3s2, 3p6 over and over and over again. This is really where things change, so that's why we want to focus on that valence portion and just keep this simple when we're writing things. But of course that's not what the question was asking us. They wanted the full configuration. Now, what we want to do, I wanted to get rid of that, and we're going to rewrite the vanadium here. Just a second. In the abbreviated fashion. Okay, now because vanadium is a transition metal, we have some different rules when we're trying to decide how many valence electrons we have. So the valence electrons, those added after the noble gas configurations, in transition elements, so this is for the transition elements, include the ns and n-1d electrons. So we want the highest s electrons, so that's this guy, and the one that is n-1, so 4 minus 1 is 3, these 3d orbitals. So both of these superscripts are indicating valence electrons for us. We have to include the 4 and the 3d. So this guy's going to have 5 valence electrons. All right. Let's take a look at antimony here. Antimony is right here. It's a main group. Okay. And we can see that at this point we got some pretty small print down here, but I think we can make it out. So we're going to circle our antimony. We know we have to go up and over. So antimony SB is going to have a krypton core, and its valence is going to be 5s2, 4d10, 5p3. So 5s2, 4d10, 5p, what was the number? 3. Okay, now I want to see if maybe we can do a little cheat to get to the full configuration. I hope you guys kind of have followed along on the pattern that we're going to use here, but basically what we're going to do is we're just going to go down this row all the way to krypton, writing down each one of these, and then we're going to tack this on the end there. So we're going to start at helium, 1s2, neon, 2s2, 2p6, argon, 3s2, 3p6, krypton, 4s2, 3d10, 4p6, and then 5s2, 4d10, 3p3, this section right here. 2, 4d10, 5p3. So now we have the full electron configuration, our abbreviated electron configuration. If we come down here, this is a main group, so we're looking at just the N level. So that means that we're not counting these 4d10s anymore. We're just looking at N, the highest N level, the 5. So we're just looking at this 2 and 3 here. This guy's going to have 5 valence electrons. And I think we might start to notice a pattern here. So P had 5 valence electrons, antimony had 5 valence electrons. In fact, nitrogen's going to have 5 valence electrons. All of the species in this column here, this group, are going to have the same number of valence electrons. Finally, let's take a look at SM. SM is way down here. It's one of the lanthanides. So what we're going to need to do now is not let too much of this sway us, okay? We're going to start by writing down the symbol just like we did before, SM. We're going to write down its valence portion here, 6s2 for F6. S2 for F6. Now, these lanthanides here, they're right here. Like, this is cut off and brought down here. So to get to the core, what we're going to do, I'm just going to circle the lanthanides here. I'm going to come up and over, and I'm going to see that they have a xenon core here. It's from the last time. It's got a xenon core there. So I'm going to come up here and I'm going to give it that xenon core. Okay. After that, we would just have to write down all of these all the way down in order to get the full-on electron configuration. You're going to have to forgive me because I'm going to have to fit quite a bit in here to make this happen. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and finally the valence portion, 6s2, 4f6. If we come down here, we can see that for the inner transition elements, the n-2f, the n-1d, and the ns subshells are all valence. If we come up here and reevaluate this, the highest is 6. So these guys here count. The 5d orbitals would count, but we don't have 5d orbitals. We've only got 4d orbitals. Those are the highest ones there. And the n-2 4f orbitals are going to count too. So these guys right here are going to count. And we get a total of 8 valence electrons for that guy. And that's pretty much it. That's how we're going to use this table to be able to get the electron configuration for a ground state species.